I'm very, very happy to be here. So I have a plan. The plan is to have two sort of different parts. The first part will be exposition, some high-level descriptions, maybe a bit of technical things at the end, but not so much. The second part will be 2 or 3 arguments of some sort. And we'll see how time goes. And in the middle, we'll have a break, and you can choose for yourself. You can always choose, of course, but it's easier when I'm...
You're going to talk for 2 hours? Or?
So I thought to do about 50 minutes, then a 10 minutes break, and then another 50. And we'll see how it goes. Maybe we'll stop after 10 because it will be... So, OK. So the general thing I'm going to try to explain is how to use groups to build expanders, or maybe a very specific way that was lately used in several works that gives one answer to this question. Expanders. So first, I will start by a very brief definition of expanders. I guess all of you know them, but just to have some common language. And then we'll discuss how to use groups in general to define graphs. This is something all of you also know, I guess. And then we'll be a bit more specific. So the first part is, what are expanders? So expanders are graphs. In our case, they will either be bipartite or regular graphs. We'll switch between when it's, I will tell you when we switch. So we have some graph. And in general, there are many equivalent definitions for a graph being to be an expander. The first definition that I will use is vertex expansion. What is vertex expansion? I will explain what it is in the bipartite case. So a vertex expander is a graph with 2 color class, a bipartite graph. So we have some set A and some set B. And the condition is that every set here, A prime, that is contained in A and is not too large, so we have every set on the left not too large. The neighborhood of the side of the neighborhood of A, all the vertices here that are connected to A, is at least 1 plus C, the size of A, where C is some constant. Okay, so this is the usual definition of a bipartite expander in the vertex sense.
Here, are you thinking of A and B as roughly the same size, or does it matter?
In this definition, it doesn't matter, but yeah, in the cases I will consider, it will be the same size exactly. The second definition of expanders is a spectral definition. So what is a spectral definition? If we have a graph G, now it will be non-bipartite for this. We can define from a G the adjacency matrix, normalized adjacency matrix of the graph G. Let's call it T. So if there are n vertices here, this is an n by n matrix. And the graph G is an expander if, so we have a graph G. Let's say that it is D-regular. Then the normalized adjacency matrix, then the graph G is an expander if there is a spectral gap, and I will write just one meaning of it, the size, the L2 norm of T of F is at most lambda, the L2 norm of F, and whenever F is orthogonal to the all 1 vector, and lambda is a constant strictly less than 1. Yes, I assume that the graph is regular. And there are many variants. I'm just choosing one for this. So this is a spectral definition. And the third definition, which I will talk less about. So is it clear? I guess all of you know it, so I don't speak too much about it. Wow. The third, right? Yes. Wait. The third definition, which I will not speak too much, but it will be somewhat useful at some point, is that random walks on the graph mix extremely fast. So when we perform a random walk on the graph, we reach a uniform, if it's deregular, we reach a uniform distribution after logarithmic many steps. This is roughly the statement.
But this is not equivalent.
Yeah.
So, yeah.
If you look at the worst case starting point, it is.
So you can think of F being as the beginning distribution, and if you do it for all the unit vectors, then it's equivalent. So, yeah. So this implies this. You agree? And the other direction follows by convexity. It's not like, so I'm sure you can. It's so, but it's not very important. Just 3 points of view. Okay. So this is just expanders, and some things that all of you again know. So some comments. So most graphs are expanders. This is sort of well known. What other comments? So there is one comment about, so most graph are expanders, and then we ask ourselves, are there construction? And the answer to this, there are many construction of expanders, as you know, and usually they sort of have two flavors. So one type of construction is combinatorial or iterative in some way. Like the zigzag product of Omer, Salil, and Avi. So there are combinatorial construction of expanders, and there are also sort of algebraic construction. And I think the first construction was algebraic. So I'll give some. There is a Margulis construction. There There is the Gaber-Galil construction. There is Lubotsky-Phillips-Sarnak. And there are many more, or maybe not many, there are more constructions. But what I will talk about will not be any of these, sort of. It will be a different type of construction. So the constructions we will talk today will be sort of related to Helfgott and to Bourgain and Gamburd. So this is the type of things we'll discuss today. The third comment is maybe a short discussion. Is also, it seems to me, a natural question: how simple, and this is not a formal word, can expanders be? And simple, of course, does not have a formal meaning, but it is from the 50s. It is known that so some planar graphs are not expander. This is a not expander graph. This was yes, but the relevant statement was still yes, but who is the pair? I forgot it. No, even before that. Yes, so Ungar. So Ungar, I think, as far as I found, is the first one in the 50s to prove such a statement. But yeah, there are many improvements on this. There is Lipton-Tarjan, then Noga and some other people. I don't. So okay. So planar graphs cannot be expanders. Planar graphs are not. Another sort of question was, so this Gaber-Galil construction was a two-dimensional TOS. The underlying graph was a very simple abelian group. The question, some question that was after that construction, is there a one-dimensional abelian group in some sense? And so graphs on this group with edges with let's call it affine edges are not expanders. So graphs on the group Z modulo NZ with simple edges cannot be expanders as well. This is was proved by Clave. Yes, everything. Yeah, yes, everything I talk about is constant degree. So these are two examples of non-expanders, and lately I'm not exactly certain about the history of the problem. I learned this question lately, but some reviewers said that it was already around in the 80s. I don't really know how it completely emerged, but one specific question is, can expanders, are there monotone expanders? And now I will tell you what is a monotone expander. So a monotone. So I will now define what is a monotone expander, and then I will try to explain why I see it related to the question before about simplicity. So a monotone expander, it's again a bipartite graph, which is an expander. So first it's expander. Second, it has constant. And the second property will be the following. We can write the edge set of this graph as a disjoint union of k sets. K is constant. And we want each of these sets, E1, E2, and so forth, to define partial monotone maps on from A to B. So, yes, yes. So, so maybe I will write here A is B is the integers 1 to n, to be concrete. So there is an order on this. And so I will now write two ways to define this. So the first way is every EI defines a partial ordered monotone map from A to B. Same order. Yes. Same order.
I mean, it's just a non-crossing set of edges. Right?
Yeah, and this will be the second definition. So when EI drawn in plane, so we write all the vertices in A here, all the vertices in B here, and we actually draw the edges. It's a planar graph.
I mean, it's that it's non-crossing according to that drawing.
Yes.
It could still be planar and not satisfy.
Every matching is
so
planar.
It's that the natural drawing is planar.
Yeah, this specific way of drawing, yes, 1 to n, 1 to n. So we write the vertices, we draw the edges, this edge, this edge, this edge, this edge, and it's planar. What? Yes, so these two are equivalent, it's just two different points of view.
So
Yes.
the way they would have said it in the 80s is something like, is there an expander of constant page rank?
No, so it's not what they didn't talk about page. They didn't talk about one in the 80s.
Right.
There was the page number of the graph.
Right.
That's how they talked about it.
That's
But
what
it's not quite. It's not exactly.
It's similar.
Yes, very similar.
Yeah.
I think you're agreeing with me, even though you
It's the Israeli way.
Yes.
I mean, but if you just say it's planar, it's easy to get such gaps.
So drawn in plane in this fashion, it is planar. It's equivalent to being monotone.
But if you take any D matchings, like each of them will be.
But in this order, in this specific order. Yes. Drawn in plane, like in this order. Yes.
And you're thinking about constant K.
Yes, K is constant, independent of n. So this is, I think, a question related to this. It somehow resembles to both of these things in some way, at least the way I. So it's clearly related to being all graphs respect the same planar embedding, sort of. All matchings, all sub-matchings. And we'll see actually a more concrete connection to the question Clave answered. But these are monotone expander. And so, okay, so the answer, are there monotone expanders? So the answer to this question is yes. And it has at least two phases. So first, there was the construction suggested by Bourgain, and then we make the proof work. So this is the short answer to this question. And again, I want to maybe a remark, or maybe remarks, a few remarks. One is natural distributions on monotone graphs don't yield expanders. So as opposed to the non-monotone case where most graphs are expanders, in this case, natural distributions on monotone graphs don't yield expanders. And this is somehow related to this result. Why? Because natural distributions on monotone graphs give sort of linear transformations.
So you're saying you look at the sort of distributions of the distance between your node, the node, and all of its neighbors. Look at that set of distances, and that has to vary widely from node to node. It can't be very symmetrical.
Yes, yes.
I think that's the common reason, right?
Yes. So, yeah. A second remark is that Zeev and Avi showed that existence implies explicitness. So if someone proves that there exist monotone expanders, then we can also explicitly construct them. This uses sort of this iterative idea. So you go to a universe of size log n or something like that. You look for your graph, and then in constant number of steps, you return to the real size. So this is another remark.
That's not constant degree. No, this is constant degree. There's another explicit construction with log star degree.
Oh, I see.
But this is if you add some existence proof as constant degree expander, then you would get
And you get log star explicit?
yeah.
You need existence proof only for some small enough, or
An infinite family.
and
Every finite graph is an expander, like unless it's non-trivial. Like every non-trivial finite graph is an expander. So this is the second statement, and the third statement is that this is actually explicit. This is actually, and I will try to explain in what way, actually very explicit.
The constructions in BY.
Yeah, this construction is, there is some nice phenomena going on, which makes it very explicit. What?
How small can you get K?
Constant. So,
Can you show you can't get k equals 3?
I don't, at this point, I don't know how to prove any such statement. It's not unreasonable, I think.
Or you think you can? Or?
I know, I don't know how to prove it. But sort of 7 maybe. Like maybe the answer here is 7. But this is not, I don't know if this is also true. There are many subtle issues to take care of. Okay, so this is, how are we? Pretty good.
Maybe I should add one remark to your set of remarks, is that it follows from this construction also that there is an explicit construction of what's called dimension expander, which I will not define, but over any field, which was another problem.
Okay, so I will add, so what Avi said, that this monotone expanders yield dimension expanders. Dimension expanders are linear algebraic extensions of the usual notion of expanders. I will not formally define it, but we get dimension expander over any field. And maybe if we're talking about over...
By result of Dvir and Spielka.
Yes, this is implicit in the work of Dvir and Spielka. And it's very, very simple, the implication. And if we're talking about it, over the real numbers, Lubotsky and Zalmanov proved that any expander, and any is sort of expander, works in this. Over the real numbers, every expander yields a dimension expander. This is sort of correct. Over finite fields or any fields, we just know that monotone expander yield dimension expanders. And maybe if we are already on this, a fifth comment is that as Evan Avi showed that related to a Turing machine simulations, and this existence refutes some conjectures.
It's not us, I mean, it's Galil, Kanan, and Semarelli, the ones
Okay.
did all the work.
Galil, Kanan, Semarelli. Okay, so
Lubotsky's Zelmanov thing is only for group theoretic expanders or something like that.
yeah, there is some. This is the any.
Yeah, all right.
Yes.
Also, using randomness, we know nothing better about monotone expanders than deterministic. So randomness has not helped at all.
Yeah, the only construction we know is this, and the Avi and Zev.
And everything is very determined.
Yeah, now we don't know how to use random or any non-constructive value.
Could you elaborate on this fifth point here?
No.
I can elaborate, but I don't, maybe we need the time, but I can.
Yeah. Yes. Okay, so this was what are expanders, some background, and what are monotone expanders, and some background on them. And now let's talk. So this is the first part. Now let's talk about how to use groups to define graphs. So this is the second part. So the groups to define graphs, and I will use. So I will now define what is called a Schreier diagram. which I guess many of you know, but maybe not all of you know the name. So it's a way to use a group to define a graph. And if some of my notations are not clear, please say so. So to define this graph, we'll need two things, or three. We'll have a group, G. We'll have a set, some set X. And we'll have a subset of the group, S. So these are the three ingredients that will allow us to construct a graph. And it will not be just any group and set. The group will act on the set. So the group G acts on the set X. What does this mean? This is very simple. For every group element, we associate a map from X to itself. And this map respects the group structure. So the composition of these two maps is the map of the product. Okay, so this this group acts on this set. A simple example, or an example, is X is G, and T of G of X is G times X. So this is perhaps the simplest example, and there are many, many examples of this. We'll see more examples soon. So we have a group, we have a set. Now we have a subset of G. In our case, it will be a finite set. And we'll use this set to, the graph G, the vertex set will be X, and there will be some edges that depend on S. So the vertices is the set X we are acting on, and the edge set is determined by this S. And the edges are of the form X is connected to Tg of X for G in S. So every point we connect to all the other points that S sends them to. And to make G undirected, we require that S is symmetric in the following sense. That S contains all the inverses as well. So this makes this graph undirected, because if there is an edge from from X to X prime, there is an edge from X prime to X. So it's undirected.
So the special case that you mentioned above, that would be the Cayley graph.
Yes, very true.
Just make sure I'm getting the name right.
Yes, very, very true. The most common way to define graphs using groups is Cayley graphs, and this is when X and G are the same. So when X is equal to G, it's the Cayley graph. So yeah, maybe, so this is already the comments. So this is one comment. Another comment that is related to this, in this case we can have G that is much larger than X. So, and this can sometimes be useful, where we have a huge thing acting on a small thing. So this can be. And
In fact, you can have infinite.
yes. Yeah, this is true in both. So maybe we'll add 2 more examples just to be clear. The first example is G is SL2FP. So what is the group? It's the group of 2 by 2 matrices with determinant 1 over this finite field. The set X that this group acts on is the projective plane. Projective line, sorry. It's the set, the field with a point at infinity. And the way the action is defined, so a matrix G goes to T of G, which at a point X is equal to AX plus B over CX plus D. And this is when G is A, B, C, D. So this is an action of the group on the set X. So it is a map from the set to itself when we interpret division by 0 as infinity and all these usual rules. And to see that it's an action, it's not obvious, but it's simple, like just a simple calculation.
So you could also just think of it as a map as an action on just the vectors of length 2 without taking the projective. So just taking the plane rather than the projective. So and then this is saying that you can further sort of restrict is saying that there's some kind of you're dividing this action up into its orbits.
Yes, sort of, yes. So this is one example. Another example, which is very similar, but maybe a bit it's actually the same example, is, so example 2, this is 1, 2, is G is SL2, but now the entries are real numbers. This is out. And the set X is the projective line. And this, again, is an action. And everything is infinite, but it doesn't really matter.
So you're giving examples of just group acting on a set, not of expanders, right?
Yeah, so far it just, yeah. And yeah, if you ask, then we can add, let's say, two matrices, and so we can now look on the Schreier graph of G, X, S union S inverse. This is some graph. The vertices are the real numbers and infinity. The edges are defined by these maps. It's a finite degree graph. Okay, so these are examples of actions and of some Schreier diagram. And now I'll explain how. So this, yes, there is a Schreier diagram that is very similar to the second construction. So now the construction of monotone expander. So G will be SL2R. X will not take the whole projective line, we'll just take an interval, the interval 0, 1. The set S, I'll explain how to choose it. But it's a finite set, and I will say soon it's very explicit in some sense. And again?
You have to define expansion in the infinite set.
Yes, correct. So this graph, the set of vertices is infinite. So
I mean, are you going to do it through Lebesgue? I mean, through the Lebesgue measure on the.
yeah, exactly. It will be exactly the Lebesgue measure. So I will now write exactly what I mean. So let's denote by psi.
Same set of derivatives?
No. So this is
That was an example.
S example.
And that one is not one.
It's a different.
This one.
So yeah, there are many things to explain even on before trying to prove anything, but let's do it step by step. So if we denote by phi this T of G, and I will write this tilde for G in S. So every G defines a map on the projective line, as we saw there. But here we are interested only in maps from 0, 1 to 0, 1. So it will not be full maps. It will be partial maps from a subinterval of 0, 1 to a subinterval of 0, 1. Okay, so this is a family of so psi is a family of continuous partial maps from 0, 1 to 0, 1. Okay, so we have a finite family of maps. This S, I didn't explain what it is, but and the property, the theorem, for every set so measurable. For those of you who don't like it, can ignore it. For every measurable set in the interval, the size of the union of psi in psi of A is more than 1 plus C, the size of A, if the size of A is smaller than 1/2. And C is some universal constant. So this is the analog of an expander in the continuous setting. So this means if we draw 0, 1 here and 0, 1 here, then for every measurable set here, the size of the image is strictly larger. And this thing, the size of a set is the fraction inside 0, 1, the interval. And
So, if you have a mapping that takes something from inside the interval and maps it to outside, then you do what? Just ignore that portion of it?
yes, yes, yes. So it's a partial map. Yes.
And is it enough to check this just for intervals? Or do you really need measures? Do you really need lots of steps?
Oh, yeah. Like a sigma, no. It's a measurable set. It's finite intervals, but all unions of finite intervals.
It is very easy to build an expander for intervals.
And okay, so now we have a continuous monotone expander. Yes. I didn't say monotone yet. Yes, sorry.
Some question. So you said this was set of must have. So
Yes.
does this have some? Is it something to choose, or can we make it like 99%?
No, it doesn't. This doesn't matter. Yes. And now, so effect. Psi is monotone. Every such family defined by this action is monotone. So the way to see it is that if you take a derivative of this map, it's except at some. So this is very simple calculation. Taking derivative, the derivative is positive. So there is one point where the derivative is infinite, but ignoring this point, everything is monotone.
So it's a union of two monotone terms.
Yes, in our case it would be actually one, but yeah, it could be two. Yes. So
Yeah.
no, this is for every point so this means that if x is more than x prime, then g of x is more than tg of x. No, this is this one. It's this one is ad minus bc, which is yes. And yeah, and this is true, as Swastik said, only like on the connected component of the derivative being defined. Never mind. So yeah, so this is
It looks like the graph of 1 over x.
yes. Okay, so we have a continuous monotone expander at this point. So there exists a continuous monotone expander. And in fact, it's not only continuous, it's also smooth, or you can take derivatives sort of as many times as you wish. Yes.
So here looking on your group is being SL2R. So why not look on just on the percent it's positive determinant? So wouldn't that help you in some way? They're not also monotone.
It sounds right, yes. But I don't see, sort of, this group is almost equivalent to SL. So it's almost, I don't see how it can help.
So this holds only within each of the segments separately, right?
Yes, yes, you're right. Yes. And now another simple statement is that so this is a continuous thing. We want a discrete thing, so we can write let's say a lemma, or so by partitioning 0, 1 to n equal length intervals, we get a discrete monotone expander for whatever n we choose. Okay, and this follows because these maps are smooth.
How do you define it? You partition interval and then what?
You define the maps on the middle position, you see where it goes, where it lands is the,
When you're bucketing the,
yes. So sort of all of this family of graphs is obtained by one family in a very simple way. You just chop it off at whatever size you want.
So basically, you can say that you don't really, well, you don't really use the fact that it's partitioned into intervals. You basically just choose representatives in a sense, right? You just take middle points.
No, but you have to see
You
what
have
it
to see
lands
where
in
it
and
goes.
enter.
Right, yeah, but so I mean, the point you start from a point. You don't start from interval. Look where majority of points go, or something like that.
Yes,
No,
it's
you
like
start
a,
from points.
yeah, 1 point. Yes, and it's not hard to see that this this C is translated maybe to C over 2 here, but some constant greater than 0. Okay, so the only thing that we did not discuss about these things is what is this set S. After we did this, at least we stated the whole thing. So I will now tell you what is S. What is S? So there are numbers Q, Q, R. Numbers 1, 18, 15. And we look first on the, so we have one set of matrices will be alpha 1, it's 1 over Q, 0, 1. And alpha 2 will be the transpose. So very simple matrices. Beta is 1 over K, 0, 1. Again, a very simple matrix. And the set S is beta beta inverse, and words of length at most R in alpha 1, alpha 2, alpha 1 inverse, and alpha 2 inverse. So it's, you multiply these matrices R time in all possible ways. It's a finite set. This is the set S. Okay? So the entries here in all of these are like rational numbers. Very big, but finite rational numbers. So all of these maps can be computed very, very efficiently. Just you multiply by some number, divide by some number, and that's it. So in that sense, it's very explicit. The bounds on this Q, K, and R, I don't know. So you can make it maybe some number, but it will take a lot of work, really a lot of work to find the real value.
They are derived from C. You want some bound C in your expansion, and you will get some numbers QR and QK.
But even for like C going to 0, this will not improve by like.
No, I'm just saying that for. So if you want C to be 0.01, there will be some numbers.
Yes, yes. But this will be at this point huge, regardless of anything. Like it's.
It's not necessarily a sensitive function in the right way. So
Yes,
QK,
there are many
presumably
layers.
R needs to be sufficiently large anyways for you to.
So it's look like I'm even after my plan, and I just stated the whole thing. So let's recall what I did so far and then take a break. So we defined expander, monotone expander, and saw how to define a monotone expander using a group as a Schreier diagram. And in the next part, we'll discuss more about the proof, and hopefully I can explain why it will take a lot of work to figure out exactly what are these numbers. Okay, so we have a, say, 10-minute break.